Welcome to The Explainer. Today, we're diving into the invisible rules that prevent total digital chaos. We're talking about database transactions, the secret sauce that keeps your data correct, even when thousands of people are hitting a system at the exact same time.
So let's start with a question. How do systems actually manage this? I mean, think about it. You've got banks, you've got airlines. What stops two people from booking the very last seat on a plane simultaneously? Without any rules, the answer is nothing. It would be absolute chaos.
And this right here is a perfect example of that chaos. It's called the lost update problem. So look what's happening. Two transactions both read the same account balance, $100. Transaction 1 wants to deposit $50, and transaction 2 wants to withdraw $20. Transaction 1 calculates its result, $150, and writes it. But right after, transaction 2, which has been working off that original $100 balance, writes its result of $80. And just like that, the $50 deposit is gone. It just vanished into thin air. So here's our game plan for today. We'll start with this whole concurrency problem. Then we'll lay down the law with the ACID rules. We'll figure out how to test if things are correct with serializability, and then dive into how we actually control the chaos. And finally, we'll look at what happens when things go wrong, like recovering from failure, and the ultimate standoff, deadlock. All right, let's get into it. To stop that data corruption we just saw, every single database transaction has to play by 4 fundamental rules. You'll hear them called the ACID properties, and they are the absolute foundation of trustworthy data. First up is A for atomicity, and this one's simple. It's all or nothing. A transaction is a single unit. Think about a bank transfer. It's really 2 operations, a debit and a credit. Atomicity promises that either both of those happen successfully, or if something fails halfway through, the whole thing is rolled back like it never even started. No money gets created or destroyed. Next up, C is for consistency. This is all about playing by the rules. The database has certain integrity rules, right? Like an account balance can't be negative, or an order must have a customer. Consistency guarantees that a transaction takes the database from one valid state to another valid state. It won't break your fundamental business logic. Then we have I for isolation. Now this is the big one that directly fixes our lost update problem. Isolation is basically a protective bubble around each transaction. Even though hundreds of them might be running at the same time, isolation makes it seem as if they're all happening one by one in a nice, orderly line. No one gets to see anyone else's messy, unfinished work. And finally, D for durability. This is the database's pinky promise to you. Once it says, yep, your transaction is committed, that's it. It's permanent, it's written to disk. A power outage, a system crash, it doesn't matter. When things come back online, your change will still be there, safe and sound. Now here's what's really interesting. You'd think the database handles all of this, right? Well, mostly. It takes care of atomicity, durability, and isolation. But consistency? Believe it or not, that's on you, the developer. You have to write the transaction logic that respects the business rules. The database just enforces it. Okay, so following those ACID rules is pretty straightforward if you just do everything one at a time. But that is incredibly slow. The real magic and the real challenge is getting that speed and performance by mixing operations from different transactions together, all while keeping the data correct. The exact order of operations is called a schedule. On the left, you've got a serial schedule. It's safe, predictable, and slow. On the right, you've got a concurrent schedule. This is way more efficient because operations are interleaved, but as we saw, it's a minefield of potential problems. So how do we know if a messy concurrent schedule is actually safe? Well, there's a test for that. It's called conflict serializability. And the core idea is this. A concurrent schedule is correct if you can prove it produces the exact same result as some serial schedule. If you could have gotten the same outcome by running the transactions one after another, then you're good to go. And believe it or not, we can actually test this visually with something called a precedence graph. It's pretty cool. You just put a dot for each transaction. Then, anytime you find one transaction's action conflicting with another's, like one writes what another reads, you draw an arrow showing the dependency. You do this for all the conflicts, and then you step back. If you see a circle, a loop in your graph, congratulations, you've just proven that schedule is bad and will corrupt your data. So now that we know how to spot a correct schedule from an incorrect one, the next big question is, how do databases actually enforce this? How do they make sure in real time that only those safe, serializable schedules are ever allowed to happen? Well, they do it using what are called concurrency control protocols. And it really boils down to 2 main strategies. The first is based on locking. Think of it like a bouncer at a club. You need a lock to get access to the data, and if someone else has it, you wait. The other strategy is based on timestamps, which is more like a strict timekeeper, ensuring everything happens in a logical time order.
Now, the most common locking method by far is two-phase locking, or 2PL, and it has one very simple but incredibly powerful rule. A transaction has two phases. First, there's a growing phase where it can grab all the locks it needs, but the moment it releases its very first lock, it enters the shrinking phase. From that point on, it can only release locks. It can never ever ask for a new one. That simple discipline is what guarantees serialization ability.
Timestamp ordering, on the other hand, throws the whole idea of waiting out the window. Every transaction gets a timestamp when it starts. Then, the system just checks the timestamps. If an older transaction comes along and tries to mess with data that a younger transaction has already touched, that's a time paradox. It violates the logical order. So to fix it, the system just rolls back the older transaction and says, sorry, try again later.
And when you put these two head-to-head, you really see the trade-offs. Both of them get the main job done. They guarantee conflict serializability. But because transactions in 2PL have to wait for locks, they can get stuck in a deadlock. Timestamp ordering completely avoids that because nobody ever waits. But neither of these basic versions guarantees our data is recoverable, which brings us to our next set of problems.
Because, of course, it's never that simple, right? You put these powerful protocols in place to solve one problem, and they can sometimes create new ones. Like, what happens if a transaction just fails halfway through? And how do we handle that absolute nightmare scenario where everyone is stuck waiting for everyone else?
This is all about being able to clean up a mess. Imagine transaction A reads some data that transaction B wrote, but B hasn't finished yet. We call that a dirty read. Now, what if B fails and has to roll back, while A is now working with garbage data? That can set off a chain reaction, a domino effect of cascading rollbacks. So we have stricter rules, like a cascade-less schedule, which says, nope, you cannot read anyone's data until they have fully committed.
And then there's deadlock, the ultimate gridlock. This is when transaction 1 has a lock on the customer record and is waiting for the order record, but at the same time, transaction 2 has a lock on the order record and is waiting for the customer record. They're stuck in a circle, each waiting for the other. Neither can move forward, and they'll wait there forever unless the system steps in and does something about it.
To stop this from happening, systems use prevention schemes, often based on those timestamps we talked about. It's kind of like a seniority system. In wait-die, an older transaction will wait for a younger one. But if a younger transaction needs something an older one has, the younger one dies. It gets rolled back. Wound wait is more aggressive. There, an older transaction will actually wound or force a rollback of a younger one to get the resource it needs.
So let's just recap the whole thing. Keeping data correct is this amazing layered defense system. At the bottom, you have the ACID properties as your foundation. On top of that, you have serializability as the gold standard test for correctness. Then you have the enforcers, locking and timestamping protocols. And finally, you have systems to manage the side effects of those protocols, like deadlock and recoverability.
And all this leaves us with one final big question. We live in a world of massive global-scale applications that demand instant, microsecond responses. And in this world, the timeless battle between keeping things perfectly consistent and making them incredibly fast rages on. Are these classic rules of order still enough to manage the chaos of today?